So I'll just kick us off. Good morning and welcome to our webinar today, Introduction to Irrigation Water Management and Planning. My name is Jan Thomas and I'm a training coordinator with the Center for Technical Development, or CTD. And I'm really happy to be here to help host the webinar today. I am also joined by Mike Palguda, our new training coordinator with CTD. So you'll see us both out and about in these webinars and some of our networking forums and other venues. So if you're not familiar with the CTD, we are here to help provide training and professional development opportunities for district staff, as well as sort of facilitate that sharing and networking piece. So you'll see our networking forums, a newsletter, and other things to just kind of help people keep connected to these opportunities. And I just want to give a really big thank you to John for bringing us, the CTD, into these types of trainings. And put the call out to you all. If you have trainings that you would like to see, please do reach out and let us know. This training particularly was spurred by an email from a district staff person. So just let us know what you need. And we want to help get these trainings out to you. And I'm just going to put our website and a contact email in the chat there. So if you ever have anything that you want to see more training on, please let us know. Couple of logistics. We are recording this webinar this morning and it will be posted within a week or so to the CTD website in our training library section, on the Commission's Irrigation Efficiencies webpage, and also just on our CTD YouTube channel. So you can look for it later to follow up or to share it with folks that maybe weren't able to be here today. We are in a meeting format, so you all have control over your own cameras and mute. So please do stay muted during the presentation. If you have questions, we can take those anytime. Harold would like to just address those questions as they come up. So feel free to put them in the chat and I'll just let him know that we've got a question in there. And at the end, we'll do a dedicated Q&A section as well. And that'll be a good place to just raise your hand and ask your question directly if you're comfortable with that. I think that's everything I have. So I'm going to turn it over now to John Culp, who is going to get us started for the day.
All right. Thank you, Jan. And thank you, Mike, for helping us out. So just real quick, for those who don't know me, I'm John Culp. I've been with the Commission for 22 years and managed the water resources programs that the Commission has. Our backbone program for that time has been the Irrigation Efficiencies Grants Program, which recently underwent a guidelines update and to make it more broadly accessible across the state. And so, I work out of Okanagan, which is bright and sunny today, which has been a while since that's happened. So trees are budding out and the crocuses are up. So anyway, things are good. Happy to do this training today. So I am going to lead this off to just say that that these new guidelines, as with the old guidelines, require an irrigation water management plan for each of the new on-farm water application projects that we fund with efficiencies dollars. And so because of that, the Commission has adopted the NRCS standards and practices for its cost share funding. And so to that end, the NRCS practice code, if you're not familiar, for the irrigation water management planning is 449. And a little bit about that, I want and we can post these resources up in a folder on the efficiencies webpage, the practice code, and the practice statement of work has some pretty specific language in there that sets some expectations, along with the separate document that's implementation requirements. And so I encourage you after this training to go pull those up, or you can wait till I get them posted. It'll be easier. I have them on my hard drive, so I can post those up in resources so that you can take a look at those before you get to work. But also I say this because as we go through this training and then you further look at those documents, as you're planning to develop your projects, the program now has project-specific technical assistance. And so that's where you're budgeting for cultural resource assessment time, or the cost, if you hire a consultant to do that, engineering costs for pipeline projects, any of those project-specific costs that you need to perform prior to installing the irrigation system, but also in the collection of data for your irrigation water management plan. And Harold will talk about some of those upfront things. But I just say this, I want to make sure that you're budgeting appropriately to cover in-house and out-of-house time and expenses to make sure that we're getting a good quality plan. And that includes data collection post-project. So yeah, just generally, irrigation water management plan is developed to manage soil moisture to promote plant growth. So it's really about how much water you need and when and how fast to apply it. And so I did want to make note that some growers in certain areas, especially the closer you get to the Columbia Basin federal project, maybe more generally, wherever cash crops are grown, an irrigator might already employ a consultant to provide them with irrigation water management reporting and scheduling. So there's a cost associated with that to the grower, but if they're already but the return on your investment is significant enough in cash crops that they can afford to do that, and it pays for itself. And so if they're already doing that, working with a consultant, you don't need to write this plan. But I would like to have you collect the past 2 years worth of data and have that on hand and providable to me so that we can verify that they are actively doing irrigation water management and will be in the project area. And so let's see. Okay, one final, I just wanted to reiterate the questions. If you have them during the presentation, feel free to ask. There's some pretty complex things involved. I mean, it's simple once you know it, but as Harold goes through, if you have a clarifying question, ask it now, because somebody else may be thinking the same thing, wondering the same thing, and so get the question out. We can get the answer there. So you can use either the chat or the raise hand feature, and between Mike, Jan, and myself, we'll be monitoring to try and catch those in real time and get those answered and then move along. And then I did want to point out about questions post, and this will be along with the recording as well, but post training here, if you have any follow-up questions or something pokes up that's site specific that you're not quite sure how it fits into this, reach out to me. My contact information is on that irrigation efficiencies webpage on the Commission's website in the program section. And then I'll also put my contact information in the chat near the end of the presentation. So to help us understand the practice and principles of irrigation water management, we brought along Harold Kroos. His reputation precedes him, but I'm going to offer an introduction to anybody who's new to our family. As a retired NRCS, or Natural Resource Conservation Service, I'm sure you all know that, employee of 41 years, Harold is an invaluable asset to the Columbia Basin Conservation District and the Greater Columbia Basin. Today, Harold mainly assists the Conservation District as an advisor and technical specialist. He's recently taken on the role of the Odessa groundwater replacement project. Sorry, I should have written that out. I just had the acronym and had to remember what it meant. But he's the coordinator for that. He's most interested in helping expand the technical capacity of the Columbia Basin Conservation District and has a passion for soil health and all aspects of agricultural energy conservation. In his 4 decades of service with NRCS, he worked in water quality and quantity in irrigated agriculture, dryland farming, forestry, and served on numerous committees, including the national team that developed the technical guidance on wind erosion. Harold continues to be on the forefront, identifying and implementing progressive conservation practices that benefit our natural resources and stakeholders alike. So thank you so much, Harold, for giving us some of your precious time. I know you're busy, but let's create some new experts in irrigation water management.
Sounds like a plan, John. Thank you for that introduction. Appreciate it. I'll go ahead and try and share my screen now, and we'll get into this and see what we can do here. Can you see that, John?
That looks good, Harold, but we've got your Zoom.
There you go. Yep.
Okay, let me get to where I need to be here. Okay. Okay, is everybody on board with that?
Perfect. Yeah.
Perfect.
Okay. You know, we can't really start a conversation about irrigation water management or planning and for irrigation water management without having a discussion right up front about water and availability of water. And I want to start and preface this whole session this morning with, you know, this, I'm making some pretty broad assumptions here. Number one, that most of the people on this call have limited knowledge about irrigation or irrigation water management for that fact. So if some of you are far ahead of that, then please bear with me. We can always learn something by looking at stuff that we think we've known before, but maybe we'll learn a little bit more about. So, and they talked about the chat, and I like to have this to be interactive as much as possible. So please put any questions in, and so we can answer them right away. But again, the water allocation and use, and this is when you're meeting with a grower or a new person, you want to have this conversation that we're going to go through right up front. And it's, and just kind of look at the a little of the background on irrigation. 25% of irrigation water is from groundwater, and that's in this state right now. So 25% from groundwater. And with that, you know, there are areas like we're working on in the Ogwarp right now that are seeing those aquifers deplete, and significantly, to the point where those aquifers will run dry at some point. So the work we're doing right now in the Odessa is transferring those people on well water into Columbia River water through the existing canal system. So this is going to vary across the state on what where your water is coming from. So 80% of the Washington water withdrawal is for agriculture. It's a huge consumer of our water in the state. And again, that's water withdrawal. And water withdrawal can be groundwater. It can also be from streams. It can be from irrigation districts across the state, like the Columbia Basin Project or in the Kittitas Valley or the Yakima Valley. They all have irrigation districts that they can go to find out what their water allocation is for their property. Only 4% of the renewable water supply in the Columbia River Basin is consumptively used. So a little bit of the Columbia River water is used currently. The Odessa, the Columbia Basin Project itself has 3% of the Columbia River allocated for use. And in contrast, the Colorado Basin has 103% of their water allocated. And that's why we're seeing the problems with climate change, and the output from our watersheds is going down. So you can see the Colorado Basin has a lot of trouble right now. And we've been hearing about that in the news and whatnot. So it's extremely, as those areas start to go dry and puts more pressure on the irrigated parts of the country, particularly Columbia Basin is seeing some interest from growers in California and other places wanting to come into the Columbia Basin. So California has 35% of their water allocated, and Mississippi 9%, and in-stream flows will continue to be the focus of future debates. I know that debate's going on in the state of Washington, and things like adjudication for water right purposes. The Kittitas Valley went through that. The Columbia Basin hasn't yet, but I think over in the coast right now, maybe Skamania County, I'm not sure exactly, is going through that debate on water use right now. So water rights, the basics. Nobody owns water. And that's important to understand. You don't own water. You're given the right to use water through water rights. Water resources are limited. And so if you're drawing from a stream, you may have limited access to water if you can get it at all. I know in the state of Washington right now, there's a moratorium on drilling additional wells for using groundwater for irrigation. And so they're already, it's just a critical topic at the state level right now. And this is a statement they used way back in the beginning, that whiskey is for drinking and water is for fighting over. Well, we're in the midst of a lot of that fighting in certain places of the state right now for the water. DOE manages the water in Washington state. The water rights are run through the Department of Ecology. They basically set the rules for that in the state of Washington. Individual states set their own rules. So you could be in Idaho under a different set of rules, in Oregon and Washington, so it's different. Since 1917, Washington state has followed the prior appropriation doctrine, meaning first in time is first in right. And that's still in place today. It applies to both surface and groundwaters in this state. Law also states that minimum in-stream flows must be maintained. And this is a topic I'm sure John could speak to extensively, where the state has actually purchased water rights from growers for in-stream flows, and that's a whole nother topic. Water rights are typically attached to the land. And so water rights and new water rights, the water will be put to beneficial use. That's one of the criteria to get a water right. The water is available within that stream or system. There's no impairment to existing water rights. So if you're putting in for a water right that has a potential to impair somebody else, that is not going to happen. It is not detrimental to the public interest also. And this is one of the things, again, for an example, in the Columbia Basin where the Odessa Aquifer is drawing down that aquifer, which is affecting 22 communities where they're beginning to see their static levels in their community wells dropping off or having to drill those deeper in some cases. Essentially, you can buy and sell or transfer water rights, and that happens. So that is one thing that's happening. Water markets are out there. You can legally transfer from one piece of land to another. Transfer downstream, not upstream. So it does not change the seniority, first in time, first in right. And generally, there's local conservancy boards that help direct that as well. And it's from the point of diversion where you're accessing that water, particularly in the streams. And Ecology has a program where they will buy or lease surface water rights in certain targeted areas. And this is important to know too, is that if a water right is idle, meaning no beneficial use for over 5 years, you can lose that water right, can be lost or relinquished to the state. And there's Trust Water Reserve Program that is also available. I think Okanagan County is going into that right now. So anyway, any questions on water rights? This is important because this is one of the first questions you'll be asking your client that you're working with. Do they actually have irrigation rights to the water they're intending to use? Now we'll get into the actual slideshow on water. So this is an introduction to irrigation water planning and management. And as John said, this will vary across the state with the type of growers or people you're working with. I know here in the Columbia Basin, a lot of the growers use a service to help them manage their water through the growing season. And so they'll have those records available. But if you're in a place in the state where, particularly if you have a brand new landowner that you're working with that has never irrigated before, this planning and going through the planning process to get them to a point where they fully understand the capability of the system they're installing, plus monitoring that system, plus monitoring the ground soil moisture content of the soil. Those are all things that will be foreign to that individual. So this is where you, as a planner, will basically be their support. And you'll be training those people basically on how to use the system. And we don't run into this often in this part of the world, but except in some smaller landowners, those people are buying 20 acres or 5-acre pieces and want to irrigate a pasture and stuff like that. You may even be thinking about getting into some of the design aspects of that. So this is a picture looking out over Moses Lake. Here in the basin, we have several types of irrigation systems, predominantly the center pivot systems and wipers. There are, of course, in orchards and vineyards and those things, the solid set type systems and drip systems, but predominantly we see center pivots in production agriculture here. So this is pretty applicable to some things. Hey, buddy, I got an irrigation system. Now what? And the correct answer isn't, I don't know, just turn it on. That's a prescription for failure right off the bat. So, you know, just having an irrigation system and not knowing how to operate it is going to be very costly, and you're not going to get the results that you're really looking for. So irrigation, by definition, is the artificial application of water to the land or soil. It is used to assist in the growing of agricultural crops, maintenance of landscapes, and revegetation of disturbed soils in dry areas and during periods of inadequate rainfall. And this is important because if you're on the coast where you get, if you're in Pacific County, 70, 80 inches of rain a year, but let's say, you know, it's going to be there. So irrigation systems that are installed are usually supplemental water sources where rain will pick up the predominance of the irrigation, but during the driest parts of the summer, this would be a backup system. Additionally, irrigation also has a few other uses in crop production, which include protecting plants from frost. We see this a lot in our orchards over here, early season cherries and whatnot. They'll have basically two systems on the place, one with overhead impact sprinklers for frost protection, and then they'll have under tree systems for really looking at the main water supply for irrigation principles. But you have to take into consideration the water that's applied for frost protection when looking at irrigation frequency and soil moisture monitoring and those things. We also use it for suppressing weed growing in grain fields where you're putting in enough water where the grain will outcompete the weeds. In some cases, not always. It's not what I would consider 100% effective, but it can make a difference. Helping in preventing soil consolidation, if applied right, and this is a double-edged sword. You can apply water through an irrigation system that will actually create compaction of the soil surface. And this happens a lot on our heavier textured soils, our clays and clay loams, which have multiple problems, which I'll get into later. Irrigation systems are also used for dust suppression in our stockyards. We see that where there's a lot of cattle confinement. They put sprinkler systems, a lot of times big guns around the perimeter on the fences to put down enough water for dust suppression. And then also disposal of sewage for those of you who work with dairies. They'll have a system that's a combination of being able to apply the ag waste for nutrient management. And they also use it in mining for dust control, and as well as some pretty drastic changes to the landscape where they're using hydro systems for mining purposes. And irrigation is often studied together with drainage, which is the natural or artificial removal of surface and subsurface water for a given area. And I know, again, in the Columbia Basin and the Kittitas Valley and some in Yakima, if they didn't put in subsurface drainage, they would probably have real problems with artificial wetlands and those types of things. So drainage, understanding the drainage is critical. And we've also used drainage as a backup for subsurface moisture, where we've put structures at the end of drainage systems where we can shut the drain off and have the water backed up through the drainage system to supplement the irrigation systems during the driest parts of the year. So there's things we can do with water, but the primary thing is understanding what those water levels and what the water table is for your situation. So irrigation in the U.S. is less than 15% of the cropland is irrigated, although irrigation is essential for crop production in some of the most productive areas of the country. We're beginning to look at irrigation as in the light of food security now as well. Some of the areas in California that are going dry, that will affect local markets as well as regional markets. And so irrigated land is extremely important in the scheme of things as food security and providing the foods and fibers that we need as a population. The need to irrigate is usually driven by the necessity to meet the water needs of the crop. And we'll talk more about that a little bit later. In other situations, irrigation is viewed as insurance against occasional drought. In areas where rainfall is plentiful in most years, irrigation can bring benefits by reducing risk, and that's really important, meaning that a farmer is better able to control income fluctuation. Other benefits include improving crop quality. This is extremely important, and we'll talk more about timing of irrigation with stage of crop growth and how that comes into place, particularly with our vegetable crops. And significantly increasing crop yields, particularly on sandy soils, which have low moisture holding capacities. I know that in the Warden area in the Columbia Basin has the highest grain yields in the nation under irrigated. The record holders have been there, producing 230 to 250 bushel wheat on irrigated ground. So it's significant. Increasing opportunities for double cropping, planting sweet corn after peas in the same year is something we use quite a bit in the basin. So you're able to get, having that irrigation water late in the season, you can produce 2 crops. And in some parts of the country, even 3 crops. Texas is a good example of that. They irrigate year round. Providing a means of liquid fertilizer application. And I look at irrigation in 3 parts. I call it the triad. You need irrigation water management, you need nutrient management, you need pest management as a suite of practices. In order for nutrient management to work properly in irrigated ag, you need to have an irrigation water management plan, or you're going to leach that nutrient below the root zone. And same thing with our pesticides, or what we call crop protectants. Some of those require dry canopy conditions, and you can't irrigate so soon after, several days in some cases after applying those chemicals. So you have to have a discussion with the grower about their nutrient management plan as well as their pest management plan for the crops they intend to grow. And then you can tailor your irrigation water management plan to those periods very effectively. There are about 55 million irrigated acres in the United States. Irrigations are concentrated in Central California, Nebraska, the Great Plains. And again, back to the Bureau Reclamation projects, the Columbia Basin is the largest reclamation project in the United States. About 700,000 acres or so are under irrigation now, with the potential of going up to 1 million acres. So let's talk a little bit about systems. NRCS has split irrigation into 3 different types, and John kind of hit on this at the beginning. Surface practice standard is 443 for border, flood, furrow, corrugations, and sub-irrigation falls under that practice standard. And now you'd think, well, why would we even be looking at surface irrigation? Well, in the Columbia Basin, again, a lot of our crops that we grow, many seed crops do not do well under sprinkler irrigation for pollination reasons primarily and during seed set periods. So we like to maintain surface irrigation where you can, as long as it's according to an irrigation water management plan, that you're controlling erosion as well. We understand that surface irrigation to get to like 40–50% efficiency is a real reach. And that would be primarily based on soil type, length of run, how far you're pushing the water. Those types of things have to be taken into consideration. And water management is extremely difficult on surface irrigation systems. Basically, we do an effective job of irrigating the middle third of the field, where the bottom gets under irrigated and the top gets over irrigated, and they can show that, graph that out quite well. So we try and get growers to get into things like surge irrigation, where you push the water as far as you can over a set period of time, maybe 6 hours, and move, and then come back to it and keep pushing it through. With cablegation and surge irrigation practices, you can push that up to 60–65%, but it's labor intensive. And that's one thing that we'll talk about all through this, is labor is an important consideration in irrigation water management. Surface irrigation, of course, moving tubes and those things take time. Hand lines, to physically go out and move those hand lines, could take up to an hour. If you've got over 1,000 foot of length of pipe, has to be taken into consideration. So you want to talk to your growers about labor for sure, because it's an important consideration as you're planning a system. And then we have sprinkler practice standard 442, which is the solid set systems, the wheel line systems, hand lines, K-pods in our pastures, center pivots, linear, big gun. And I put on the end of this mobile drip irrigation, and I'm going to talk a little bit about that. That's the upcoming technology for center pivots. Retrofitting existing center pivots with drip lines, and we can get up to 95% irrigation efficiency without wetting the canopy of the crop. And we'll talk a little bit more about that later. And then under micro irrigation standard 441, this is point source emitter or drip, trickle, or bubbler, surface or subsurface line source emitters, basin bubblers, and sprayer mini sprinkler systems fall under the 440 practice standard. And like John said, I would encourage you to pull these standards up and become very familiar with what those standards require for full implementation. And then each of these has even more variations of irrigation methods within these types. And so, even though you're running a sprinkler system, there could be various other types, wheel lines systems, big gun systems fall under that. So there's other types of systems that can come into play, but the principles remain the same that we'll be talking about when we get into the actual planning. And it all starts with soils. It started with the water, but in your planning effort, once you've tacked down the idea that they have a valid water right and the amount of water they have, your next step is to really look at the soils on a particular planning unit that you're working with. Soil is a basic irrigation resource that determines how irrigation water should be managed. It's all managed around the soil and the soil properties. The amount of water the soil can hold for plant use is determined by its physical and chemical properties. This amount determines the length of time that a plant can be sustained adequately between irrigation or rainfall events, the frequency of irrigation, and the amount and rate to be applied. And we'll talk more about how you're going to calculate those frequencies based on soil type and crop. Along with plant, and this is evaporation, transpiration, you'll see this transpiration, you'll see this throughout this presentation, as ET is such a critical component. It also determines the irrigation system capacity needed for desired crop yield and product quality. We'll get more into that in a little bit. And I would strongly encourage you, if you haven't already used this, is the web soil survey. It's publicly available, and you can get that application on your computer. And this is critical for you to understand how to find the soils and map the soils. And we'll talk a little bit more about this in a minute. So this came out of web soil survey, and this would be a typical field in the Columbia Basin, and what you're in each number there is a soil type, and as you can see in this specific example, that a typical field has multiple soil types. And so one of the challenges at the beginning is to figure out which soil do I manage for. And the web soil survey will actually help you with this, because it'll give you the acres for each soil type listed on this map right here. And a lot of soils and fields, even though they're mapped correctly with the soil scientist out in the field digging holes and map them, they take some liberties in terms of the landscape and how often they drill a hole or how often they really look at the soil. And so there's a lot of times where you'll have what's called inclusions, or let's say this field would have been all map unit 45 and it disregarded the 168 as an inclusion. You need to be physically able to go out in the field and ground truth what that soil type is, and it doesn't have to be extensive, but when you get more proficient at it, you can actually look at a field and stand there and read that landscape and determine where you would expect a soil break to be on sloping ground versus the high points in the field. And you can get a pretty good understanding of what that real soil is and if there are any inclusions in the field. But the bottom line on this is you're going to be irrigating for the predominance, not the most restrictive. And I'll talk more about that in a minute here. So this is a typical PED-on, we'd call it, or a soil profile for a soil. And all of them have the same characteristics, what we call the O horizon, which is that organic matter accumulation that we're all striving for with cover crops and those types of things. And that's extremely important because that's where your erosion control happens. It's where most of your water holding capacity happens in that A horizon and the O horizon. But more importantly, and what I wanted to show on this is the root system. Typically in any given crop, 75% of the root mass is in the top 25% of the root zone. You're up here in this area is where the crop is taking most of its nutrients, getting most of its water. And so protecting this layer of soil here is just critical. But we manage water for the root zone of the crop. You know, it doesn't make any sense to be filling this profile up and looking all the way down here to what the parent material would be and thinking about controlling water at this depth. We just don't do it. Typically, on most of our crops, we're controlling water in the top 24 inches of the soil profile. And more importantly, probably in the top 12 inches. So it's just kind of a rule of thumb that we use, but it's scientifically accurate to do that in terms of managing water in a soil profile. And we'll get a little more into that here as we go through this. So this is typically for a soil, what you would see the depth, like a Freda series, 0 to 9 inches. And it gives you what the percent of depth of sand and silt and clay is in that section of the profile, bulk density. But more importantly, when we get into this, we're looking at the soil series and right here, available water soil capacity. And this is how much water the soil will hold in, like 0 to 9, it will hold between 0.1 and 0.3 inches per inch of soil profile. And you say, well, wait a minute, that's 0.1 to 0.13. What do we choose? Somewhere in between or whatnot. I go right over to this section. How much of that is sand? What percent is silt? And what percent is clay? And you can see here the sand is really an important part. And so in this case, I wouldn't use the higher number. I would use the lower number, 0.1, because that's going to give you a little bit of edge on the system. You know it's not going to hold that much water in here, but you want to use the lower amount. If you go higher on this and it's more sand, you're probably really not holding or being able to capture that 0.13. And this changes all through the profile. You get down here in the bottom part, look how little that'll hold there as well. But again, you're managing for this top 24 inches. So right in here in this zone is what you're managing for. So in this case, I would probably use, looking at this, and here I'd use 0.12 is probably a safe bet on this soil. The potential for a soil to hold water is important to designing and managing the irrigation system. Total water held by a soil is called the water holding capacity. That's WHC. However, not all soil water is available for extraction by plant roots. The volume of water available to plants that a soil can store is referred to as available water capacity, the AWC. Field capacity. This is the amount of water a well-drained soil holds after free water has drained because of gravity. If you're looking at a cup of water, it would be full to the brim, and any more you put on there, either it's going to run off out of that cup or it's going to go through the bottom and leach through the bottom of the profile, taking the nutrients with it as it goes. So field capacity is important, knowing how much total water that can apply. And I'll show you how you're going to calculate that in a little bit. But field capacity is a really important consideration. And then on the other end of the spectrum is what's called the permanent wilting point. This is a soil water content at which most plants cannot obtain sufficient water to prevent permanent tissue damage. Basically, what this is saying, the water is being held tighter to the soil, the remaining water held to the soil, than the plant's ability to draw that water off. And so when you get to this point, if you get to this point, you've pretty much damaged your crop. The upper limit, wet, is the field capacity. The lower limit is dry. is the permanent wilting point. The difference is available water capacity. So when it's totally full versus when it gets down to a percent, you've decided to draw it down to. The difference between those two is how much water is in the holding capacity, and it's going to dictate how much you apply in subsequent irrigations. The following is the soil physical properties from a local soil, and it asks what is the soil water holding capacity for the top 2 to 3 and 5 feet of depths. So as you can see here, this is a Warden silt loam, and this is one of the best soils we have in the Columbia Basin. So depth 0 to 6 inches, sand 6%, 21%. You can see versus that other soil I showed you, 60%, 68% of this soil is silt loam, which holds a lot of water. 8 to 12 to 15% is clay, which is very small. So available water capacity is shown here, and we'll go to the next part. So on a Warden soil, 0 to 6 inches holds 0.19 to 0.21 inch per inch, or when you do the calculation, 6 times the whatever number you choose would come out to be 1.2 inches can be held in that points and that top 6 inches. From 6 to 26 inches, you could hold 3.6, and down to 60 inches, 6.8, or a total water holding capacity of that soil would be 11.6 inches. That's a very simple calculation to do. So this soil would hold up to that in the top 60. So not all soils are as good as Warden. Most are not. So what do you do when you have a soil like this one? And I'll show you in a second. Which soil do you use for design, and what is the water holding capacity of that soil? And that gets back to the one I showed you here to run you through an example. And here's the profile for that soil. For all the soils you just saw on that screen are listed out here. And you can look at each one of those soils independently and get the characteristics for it. And then you can plot that out on a chart like this. You can take the soil depth for a soil series, and soil number 1, number 2, number 3, how many soils you have, and you go back to the previous slide. You'd pick every one of these soils out. You determine how many acres there are in each one of these soils in the field, and that way you can begin to see what you're going to use for your primary soil. And again, they're going to be composites. You can put a composite together for the field. But again, this is going to tie back at some point to how much water your irrigation system has to apply to meet that need. So in this case, what soil would we pick? So, and I don't have time to go through a complete example of what that would be right now, but it kind of gives you an idea of how to do that. The second part you're going to look at, now we know how much water the soil is going to hold. Let's say it holds 2 inches of water, and you're going to have to put that back on. So you really have to start looking at the soil intake or water infiltration rate for that particular soil that you picked. And this is extremely critical, especially when you're looking at center pivot irrigation, where with a low, your center pivot irrigation operating at a certain percent, like at 0% or 100%, we'll talk about that in a little bit, can apply water in a range of levels based on the speed that system is moving across the landscape. The faster it moves, the less water you're putting on per pass. The slower it moves, the more water you're putting on. There will be a point on this soil at the slowest amount you can move this system at where you could actually get runoff from a soil like Warden silt loam, especially if there's an end gun. You're putting water on so slowly that it doesn't have chance to infiltrate in the soil. It just can't take water in that fast. And this is where you'll see runoff through your wheel tracks that are left in the field, and also through the bottom of the field, where we can actually pick up significant erosion from those events. So knowing how many inches can be applied, and there's the infiltration rate is critical. So infiltration rates change during the time the water is applied, typically becoming slower with elapsed time. The typical decrease as the irrigation season progresses because of cultivation and harvest equipment. The other thing that you're going to want to talk to a grower about before as part of your irrigation water management planning is what type of tillage operations did they use for their crop. And getting back to the Warden silt loam that has a pretty high percentage of clay in there, if they're plowing that field, you can actually create a plow pan, a impermeable layer where it compresses that soil at about 8 inches deep. And that will be a restriction to the soil's ability to take that water in through the entire profile. So if that grower tells you that, yes, I'm plowing that field, then I would take them out in the field after that event, after they've planted the crop, and I'd take an auger and I'd drill down till I hit that hard pan and find out what level that's at. Because that's going to be a restrictive layer, not only for water penetration, but root penetration. In fact, if a grower told me they're going to use a plow, I'll oftentimes recommend that they follow that up with a chisel operation. I know we don't want to do more tillage, but in this case, fracturing that plow pan will be very important to the success of that crop. You get into things like growing carrots and those things that will hit an impervious layer, and they will actually stunt the growth of that carrot at that point. So it's very important for you to understand those principles. And this is also especially true if operations are done at higher soil water content. And like right now in the Columbia Basin, the weather's getting a little warmer. The sun's out, and last week I was out kind of driving around and I see people in the field actually doing farming operations now, which is fine on certain soils, but I will guarantee you that we had a lot of rain this spring and those soils are fairly well saturated and they could be setting themselves up for plow pans or tillage pans. And so it's important for a grower to understand they shouldn't be doing these tillage operations until the soil moisture content is below 50% in that field. That'll give adequate dryness in the upper parts of that soil profile to prevent that from happening. And they'll be more than satisfied later if they put that operation in there. Preferential flow paths such as cracks and wormholes influence infiltration and permeability. That's why we like to see that organic layer in that upper part of that profile and building that organic matter where our biological effects in that soil, the worms and the critters that live in that are really helping with that infiltration and not increasing it to the point where it become a problem. But we want to see that biology increase in the upper part of the root zone. In the Columbia Basin, our typical soils have 1% or less organic, and we're trying desperately to build that up. And it takes a lot of time to do that. I've been working out here 30 years and gone back to fields in 30 years that have gone to 1 to 3% organic in that period of time with pretty good husbandry practices, cover crops and stuff, and putting their residue in the right place at the right time. So it takes time, but it's going to save you in the long run. So here's some of the intake rates by surface texture. So if you're in that clay area, you can see under sprinkler irrigation, the infiltration rate is 1/10 of an inch to a quarter, 0.4 inches of infiltration rate. And that's pretty low as when you look up at our loamy fine sands and sands, where you can get up to 1.5 inches infiltration rate on those. And of course, for furrow, it changes some and border irrigation. But this kind of gives you an idea as the soil texture changes, the infiltration rate goes up significantly in those soils. So if you're irrigating a coarse sand, and I've seen some of these go up to 4 inches an hour, the intake rate on these, you're taking all that nutrient with it. And so that's why we talk in nutrient management about split applications, spoon feeding the crop. You're basically putting more nutrient on as the crop grows and the root mass increases. Lighter irrigations earlier in the season. So that all plays together. The soil type, the infiltration rate, the water holding capacity of that soil. You're beginning to see kind of a process that you go to think about these. And I can't overemphasize the necessity to look at all these and be able to talk to this subject at your first meeting with a grower. You know, you do your homework, pull up the soils, have them give you the location of the farm, pull the soils map on those, and look for those critical factors in there that could be restrictive or create management problems down the road. Like if I see a field that's all clay, I'm beginning to think of what type of irrigation system I got to put on that. You know, we don't see that over here, but on the coast, I know you do. A lot of heavier texture soils over there. So this kind of gives you a ballpark. You go to the web soil survey and it will tie this down a lot tighter. But for a rule of thumb, this works pretty well. So the intake rate can also be affected by the organic matter we talked about, the surface residue on the field, you know, that's going to hold that moisture or hold that from running off the field, just like you would in dryland agriculture. If you got residue out there, your erosion potential goes down. The vegetation canopy is so important too, can affect it. You know, when we get into talking more about evaporation, transpiration, we lose most of our moisture during the vegetative stage of the crop because the crop leaves, the plant itself holds a tremendous amount of moisture on its surface that evaporates off and never gets to the soil itself. And so you have to look at that through the growing season as well. Slope of a field, I talked a little bit about that earlier. This for sure comes into play with surface irrigation systems. Anything above 1% slope without proper protection, you're going to start picking up erosion on that. We do have ways to mitigate for that using polyacrylamide, PAM, and stuff to reduce that erosion rate. But slope is an important characteristic. And even on, like I said, center pivots, you get on a lot more slope on your Warden series soils with an end gun. The potential for erosion or runoff is high. Compaction I talked about, or hard pan. And you're going to find this in some areas like the Shano series soils where there's a caliche layer at about 18 inches. That's impenetrable. So you're really only working with 18 inches of soil for plant growth and water application. So understanding that those hard pan layers can be on some of our soils, and they're typically up on the sides of on sloping ground because over time a lot of that soil is already eroded off and is lost to production. And you can see places where a concrete ditch is sitting 2 or 3 feet above the field level because it's eroded that much over time. So it's a critical thing to look at. Texture, of course, gravel or sand. Crusting on the soil surface is something to pay attention to. Sediments in the irrigation water. If you're pulling water out of a stream, or in some cases even ponds that have wind action to stir up the sediments, that can be a problem for your irrigation system, wearing out your nozzles and those types of things. But we'll talk a little bit more about that during operation and maintenance part of this program.
So Harold,
yeah, go ahead.
Yeah, backing up to texture real quick. Renee has a question in the chat. Is the soil texture chart in the web soil survey?
Yes.
Awesome. Thank you. Yeah,
you can pull all that. The textures will be in web soil survey. There's so many things you can pull on soils. Find your way into that and start looking through it. We should actually have a session just on how to use the web soil survey, you know, and how to find stuff easily. And there's just so many functions in that that are, you know, I couldn't design an irrigation system without it. I could, but it wouldn't be as good as the one I could use it with. So be very familiar with that. Soil structure we talked about, ripping I talked about, erosion I talked about, water content, soil depth, and the chemical reactions. Now, this is really an important thing too. As over time, we've been irrigating the Columbia Basin about 70 years now, and we're beginning to see some salt issues in our soils. And and it's even been compounded more by when we went to higher efficient systems like sprinkler irrigation. You know, I've worked with growers out here that post irrigation, I'd go out in the field and actually set terraces in the field, water basins, where at the end of the season, they'd fill those basins full and push that salt out of the profile down to the drainage system. We also pick up saline soils where there's poor drainage, subsurface drainage. And so that become a real problem. You say, well, why is that? Well, if you got a salty field, saline soil, you're not going to be growing beans on it for sure. There's certain crops that really can't remove the water from the soil if there's a saline condition. It's just chemically impossible for them to do that. You run into sodic soils, that is basically make the surface texture of the soil won't even take water. It will puddle up in the field. We don't see a lot of sodic here, but there are places on the coast that you could run into that. And of course, acidity of the soil. And a lot of this has to do with how they manage their nutrients, because over time, the residuals of some of that nutrient can compound some of these problems. So soil testing is absolutely critical to water management as well. Take soil samples, understand the chemistry of the soils, have those tests run, because that's going to be so important in your nutrient management, when to apply the nutrient and how much for the specific crop or crops you're growing. So we'll talk a little about crops. The purpose of irrigation is to supplement natural precipitation so that moisture requirements of crops being grown are met. When you live in the desert like we do, your native vegetation requires only 3, 4, 5 inches of precip a year. You can see why we need irrigation to do what we do here. On the coast, maybe not so much. Crop response to irrigation varies with soils, the fertility of the soils, the type of plant you're growing, the stage of growth of that crop, and the local climate, of course. And we'll talk more about how to get around that. Knowledge of how plants respond to and use soil water throughout the growing season is essential to successful design and managing an irrigation system. Critical water periods. Plants must have ample moisture throughout the growing season for optimum production and the most efficient use of the water. This is most important during critical periods of growth and development. Most crops are sensitive to water stress during one or more critical growth periods in the growing season. And moisture stress during a critical period can cause an irreversible loss of yield or productive quality. And I'm going to show you this table 3.1 is an example of some crops' critical growth periods. And this comes right out of your irrigation guide. And I didn't mention that before. Washington NRCS has an irrigation guide for the state of Washington. I would download that into your system and become very familiar with it. It has everything I'm talking about in here and a lot more. So if you look at alfalfa, a critical period at seedling stage for new seedlings, just after cutting for hay, and at a start of flowering stage for seed production. If you're in a deficit during any of these periods of time, you could have some real problems. And when I put cutting for hay in here, and I kind of added that into here, I grow hay here, and I have a wheel line on it, and I make sure that I have a full profile of moisture before I cut hay, and then I wait a couple days and cut the hay. Because if you cut that hay down and it's laying on the ground and you're waiting for it to dry to bale, and you get a rain, let's say, that gets it wet and it pushes it out further, the chances, if it goes out, like if your irrigation frequency where I'm at is 3 days and I got to get back over it in peak consumptive use, and and I'm out there 5 days and I get the hay up and I got to come back and irrigate again, I'm not going to catch up. I'm not. I'm behind. Even though I fill the profile, you're just not going to catch up with the system you've designed to apply water every 3 days to that crop. So it's very important to understand the agronomy behind the crops you're planting in some of those critical stages. So not all irrigation systems can be used on every crop. I mentioned that a little earlier, that we don't like to, in fact, growers would not put a sprinkler irrigation system on seed crops. It just isn't done. So that's one case where you'd be very restricted in what irrigation system you can use. And some crops have distinct issues that the irrigation system must have, or the crop can be adversely affected. And the reason why we're looking right now at that mobile drip irrigation system is because that system puts water right on the soil surface, and it doesn't wet any of the canopy of the crop. And in potato crops specifically, if you start wetting the canopy of that crop, it promotes disease issues. That moisture on the plant surface coupled with temperature is a prescription for disease problems, which would require more crop protectants, pesticides, and stuff to affect that. So the more we can get the water close to the ground and on the soil surface and not wetting the canopy of the crop, the better we are. And for example, seed crops generally need to handle sprinkler irrigation. I talked about that. Or look at wheel lines don't work well in corn. So the guy comes in and says, well, I want to put a wheel line this and I want corn. Well, you can't use a wheel line on corn because it grows up and you just couldn't move the wheel line through that. So some crops lend themselves well to sprinklers. Other crops, and wheel lines is one example, would not do well in corn. And you couldn't use a wheel line, I'm being a little silly here, but in orchards and things like that, which would be pretty common sense, I guess. An example of the adapted irrigation methods for crops, and we'll look at this. In the irrigation guide again, shows each crop, or most of the crops we grow, and what type of irrigation system could be used on those. And you can see that some of those do well under sprinklers and some don't. Some do well, whatever. But kind of gives you an idea of the type of systems you could have on different crops, and that's in the guide. So that's one more tool that's very helpful for you. Now we're going to get into the management of the water, and I put this in here because people can remember Mad Magazine back, and they'll remember this concept is the management allowed soil water depletion. And this is absolutely critical in designing your irrigation system. How much water, the maximum allowed depletion of water in that soil profile before you have to come back and irrigate. And that's illustrated in a percent. So Matt, determining when to irrigate a specific crop requires a selection of a management allowed depletion of the available water soil. MAD is defined as a percentage of the available soil water that can be depleted between irrigations without serious plant moisture stress. And MAD is expressed as a percentage of the local available water content the soil will hold in the root zone. A soil water deficit in inches, or allowable soil water tension level, and we'll talk about that when we get into the type of sensing devices you can put out in the field to help you schedule your irrigations. Okay. Remember when I talked about stressing a crop during versus different stages of growth? Well, this is the control is a perfect crop. You got adequate water through the growing season and had no problems. If you're in a moisture deficit during the 5-leaf stage, you can begin to see that corn plant. It's curving a little bit and it's a little bit shorter. It hasn't filled out the entire plant, the fruit. And if you get into the 12 leaf stage, you begin to see that corn getting smaller and smaller. And if you're in pollination stage and you're going to a deficit, this is what you could end up with. You might as well take that crop out. And then during blistering, soft dose stage, hard dose stage, full dent, and mature. So it just gives you kind of a visual representation of what can happen if you stress that crop during different growth stages. And every crop is unique in that. So that's where the agronomy comes into play. So this is kind of a diagram of what MAD looks like, management allowed depletion. So when irrigate each time the soil moisture reaches the MAD level. So you can see here, drainable water. This is field capacity. We talked about field capacity where the soil is taking in all the water it can. And if you overfill that profile, the water that you're trying to put on will run off the field. It just can't take anymore. And then in this case, for this crop, we said the management allowed depletion is 30%. So when we use 30% of the water in that soil profile, we want to come back and put that 30% back on. This would typically be a sandier soil that doesn't hold a lot of soil moisture. And so you're really going to have to manage that a lot closer. Your frequency of irrigation is going to be a lot closer. Here in the basin, in the Black Sands area, we basically have to, the management allowed depletion at 30%, we have to be back over that ground every 3 days. If we go beyond 3 days, the plant's starting to suffer from that. And you can see here, plant available water in this case is all the way down to the wilting point. We say we showed you that chart earlier, what the wilting point would be. So we're going to fill this whole profile and keep it, but we're really going to manage for this 30%. So it's wet to dry. And so we use MAD. Option 1, estimate soil moisture, and option 2 is to measure soil moisture. So we can estimate it for planting purposes with your grower prior to the irrigation season. You basically estimate using the soil survey, like I showed you, that it looks like it would be about 3 days. And this is so important when you're also designing a system. Let's take wheel lines, for example. Take a 30-acre field. And a wheel line, if you have one wheel line on that field, will irrigate, let's say, 2 acres on one wheel line. And your irrigation frequency is 3 days, and you got 10 acres, your system can only get across that in 5 days. You'll have to put another wheel line on that field to meet that irrigation frequency. So if you have one wheel line on that 10 acres, it'll dry. By the time you get back to irrigate again, that you're already putting your plant in stress. And if you put 2 wheel lines on there, you can meet that irrigation frequency. So it really comes into play on how many hand lines, wheel lines, and even on your center pivot where you can adjust the speed of travel. If 3 days is a max you're going to go, then you're going to have to cover so much ground every 24 hours. And you're going to adjust your control or your speed of that center pivot to accomplish that. And again, it's going to have a certain precip rate at that speed, and you want to make sure it's not exceeding the infiltration rate of that soil. So there's all those different factors that come into play when you're designing a system versus managing a system. I don't expect that many of you will be designing a system, but you're going to be managing a system or helping that grower manage the system. And the first thing you're going to find out is what that system's capability is of meeting the peak consumptive use of that crop. So if they bring in a design to you for a wheel line, one wheel line on that 10 acres, it's going to fail. It's going to fail right away. So you're going to have to take that into consideration and say, I'm not going to cost share on this practice because it's not going to meet the needs of the crop. And you're going to say, in order to meet the needs of that crop, you're going to need 2 wheel lines out here. So there's a lot of this stuff that ties together that can be handled during your first discussions with a landowner on the type of system they're looking at, the crop they're going to be growing, the soils, the holding capacity, the irrigation frequency. That all comes into play during the planting stage. that you're going to be looking at that, and you do your homework using web soil survey and some of the principles I'm talking to you about now, to be able to speak intelligently to that landowner about what they're planning to do. That's water management, really, in a nutshell. Evaluating the system performance, understanding the crops, understanding the soils in order to best manage the moisture and what type of system to put on the land. So here, again, out of the irrigation guide, table 3.3 shows the different crops and what the management allowed depletion would be for that crop stage. So if you're on garlic, you can never let that soil profile go below 30% ever. You're going to have to get back and put it on. Small grains during flowering stage, again, that would be that's where you would design that system, right? And when it gets down to 40%, you're designing the system to meet the peak consumptive use for the crop you're growing. So you would be pulling this table and be looking at garlic at 30%, dry beans at 40%. So it just kind of gives you an indication of what those maximum allowed depletion levels would be for a specific crop in order to manage that water and design your system. We talked a little bit about this earlier. The rooting depths vary by stage of growth and should be considered in determining the amount of water to be replaced after each irrigation. You're going to find, as I present stuff, I like to tell people things 3 times. First time, you kind of get it. Second time, I think I got it. And the third time, you'll get it and know where to go. So if I'm redundant, then going over these things a couple times because it's important. All plants have very shallow roots early in their development period. Therefore, only light and frequent irrigations are needed. You know, I like to go into the season, like I said, with a fairly full profile, allowing a couple days in there. So, but when you're putting a seed out there, and some of our seed crops where you're planting that a 1/4 inch deep, think about that. And if that seed starts to starts to go into growth and it dries out during that period of time, you could theoretically and practically lose that crop. So you're going to have a system that can keep that surface moisture fairly constant. And getting back to center pivots, and this is a good example on center pivots, when they run those pivots on a complete pivot and stop it in the same place every time, half of your irrigation is happening at night and half of it's happening during the day. The consumptive use during the day and evaporation is a lot higher than it is during night. So if you're stopping the same place every time and you're irrigating half your field at night and half during the day, half of your field's going to be underwatered and half of it's going to be overwatered. So what I tell growers to do is never stop your pivot in the same place. So you optimize night and day periods of application. And it's pretty critical during these early stages of growth. So on a center pivot, if you're going to run it at as fast as speed, you want to be able to get across this ground in order to keep that surface as moist as possible, if that makes sense. Because roots will not grow into dry soil, soil moisture outside the actual root development area is needed for the plant to develop a full root system and soil profile. And here's another situation that you may run into if you're in orchard country. I ran into a situation years ago where a guy went from overhead sprinkler irrigation to under tree micros with a mature orchard crop. And he lost about 50% of his production in the first year and put on a brand new irrigation system. And, and they called me in to take a look at it. What's the problem? Well, you look at an orchard tree and you look at the drip line of the canopy. You need to get water out to that drip line of that canopy to keep that crop, a mature crop, going. When they put the drip lines in, they didn't put enough emitters on there, so they could never get moisture to go out to the drip line. So all the roots on the extending out to that drip line died. And so basically that crop was in moisture deficit for the amount of growth it was a mature tree. So the reason I bring this up is that if you have a grower come in and want to convert for some of these types of systems to another, you better make sure that they're putting that system in to cover the original water pattern of that crop, or you can run into some real problems. So we doubled up on the emitters on that and moved some of them out away from the tree, and it took 3 years to bring the crop back to where it was initially. So those little things you need to pay attention to, and it all comes back to that rooting pattern of that crop and the moisture allowed depletion and water holding capacity. So it all plays together when you're looking at these. And again, you look at that during the planting stage. And excess moisture in the root zone will also limit root growth development. And I look at this as a water table function. If you're in a poorly drained field and they haven't put any subsurface drainage system in, this could come into play and affect that root zone. Your web soil survey will give you an indication of what those soil, the water table level is for that particular area. So pay attention to that as well when you're in the pre-planting stage of the process. And table 3-4 shows typical rooting depths for some crops. So I put some of these, this again is in the irrigation guide, and it shows what those rooting depths are for the predominant crops that are growing. And that is, again, when you have that first conversation with the landowner, you're able to say, well, you're growing beans and they have a rooting depth of 2 to 3 inches. And then I stop them and say, is that the only crop you're ever going to grow? And if they say, no, in 2 or 3 years, I'll be growing alfalfa. Well, that's a whole different root growth. So you have to look at the entire rotation, what they're growing in, and you need to design for the most critical. And I say you design the most critical for water application for the crop with the most demand, but you develop your water management plan for the least. Does that make sense? I hope. You know the system will put enough water on for alfalfa, but in the year that I'm growing carrots that only has 2, I'm going to alter the speed of my system or the set time of my system to only water the root zone. So, and this is going to be another one if you run into with center pivot or wheel lines and hand lines. You know, they're typically set up either for a wheel line on 24-hour or 12-hour sets. And it makes, and again, this may, if they're on 12-hour sets and there are 60-40 spacing, on 24 hours, they only cover 60 feet. If they're going 12 hours, they can cover 120 feet in 24 hours. So that gets back to that irrigation frequency thing. But you design your system for the most consumptive use crop. You manage your system for the least. If that makes sense, because your least would be the most critical part to keep that root zone and not leach nutrients. So if it's designed for alfalfa and you keep watering like it's alfalfa, you'll leach your nutrients and you'll have problems with it. So this is important, very important to pay attention to this part of it. Root distribution. For most plants, the concentration of moisture absorbing roots is greatest in the upper part of the root zone. And it's not just, as I mentioned earlier, not just for moisture, but that's where your nutrients are being taken in by the plant as well. So you're really managing that top quarter that I talked about. Back to me telling you things 3 times. Extraction is most rapid in the zone of greatest root concentration and where the most favorable conditions of aeration, biologic activity, temperature, and nutrient availability occur. And this gets back to that temperature issue. Typically, what I call biologic zero in soil temperature is 50 degrees. We really don't want to be planting anything below 50 degrees because you'll probably not germinate effectively. And so I look at that temperature and that scheme, and I'll show you how to get that in a little bit. But it's extremely important to understand that the rooting depth of that crop is just critical. And water also evaporates from the upper few inches of the soil. Therefore, water is diminished most rapidly from the upper part of the soil. except in the cases where we're no-tilling and we're keeping residue on the soil surface. That will minimize this evaporation issue, and plus get around things like wind erosion. If you're planting a crop in the spring in the basin and you've left no residue, and you got an onion plant or a potato plant and you get a big wind, the soil can actually cut those plants off through saltation. So it's important to keep residue. All these things play together. You can't do one without the other. We're talking about designing systems here where the soil, the water, the animal, the plant all come into play, and they have to work in unison, and they have to work together to get the most positive results. And this creates a high soil water potential gradient. Figure 1 throws some examples of root development for different crops. And here's, again, in the table, you can get kind of an idea of the rooting depth. And getting back to that concept I was telling you, look where the major part of the roots are in most of these crops. It's right up in this area. So you're really managing that top part, that top 2 feet in every case that you're looking at here. It's just something that you can't go wrong with if you're managing that level. The one thing about corn is it's a little bit different critter. You can push water a little bit more on it and its roots penetrate down. And when we were designing systems in the 70s, they were telling us that the root zone on corn was basically 3 feet. And we started digging holes and we found roots down 9 feet on corn. I like to use corn in rotations because it'll reach down and grab some of those nutrients that were leached out of the profile. If you're growing potatoes and you come with corn later, you can take advantage of those nutrients that were lost in that corn crop and mine those excess nutrients in the lower part of the profile. So you can use crops to benefit for sure. Crop irrigation water requirements. There's over 30 different methods used to calculate the amount of water used by crops. The primary factors that goes into these will include temperature, relative humidity, precipitation for sure, solar radiation, and this kind of, I'll talk a little bit about solar radiation here for just a second. For you soil scientists out there, you'll know. We've done some testing in the fields of bare ground conditions and soil temperatures at seeding. We've measured bare soils during a day that with temperatures get up to 80, we can have soil temperatures at the surface up to 125 to 130 degrees. And it's something to think about on timing of planting and cover available. I'm keep building a case for residue management because bare ground can be a real heat sink, and that really affects your water holding capacity and frequency and evaporation and all those things. So soil temperature is just a critical thing. Wind is a big one too. And wind comes into play in several places. I'd mentioned one early in the season where wind erosion can basically destroy a crop in its early growth stages. But wind also comes into play for what we call uniformity of application. If you've got a center pivot with or an orchard, anything with impact sprinklers sitting 14, 15 feet off the ground, and you get a high wind, your coefficient of uniformity of applying water evenly across that field has just gone to heck. And it's critical. So we've, over the years, keep dropping those nozzles down closer and closer to the soil surface, where now with MDI, we're right on the soil. And that really helps your coefficient of uniformity because it can be a big factor in growing a crop for sure. So just keep that in mind. In hours of sunshine, I talked about this earlier with center pivots, never stopping them in the same place and having half irrigated at night during the day. But it also has to do with your growing season, the amount of days of growing season you have in the northern parts of the hemisphere is less than in the southern part. So hours of sunlight for the crop you're growing is important too. So it isn't, we're in a pretty good spot in Washington for that. And you can go to there's charts and maps that shows you different crops and how they do with different levels of sunshine. And the crop coefficient, and we'll get into that a little bit more. Each crop has a coefficient assigned to it for how it takes moisture, how much moisture it actually takes. So before we had soil monitoring devices for soil moisture, we used a thing called evaporation pan, where you'd set an evaporation pan. You could measure the amount of evaporation over a 24-hour period. You could apply the crop coefficient to that, and it would tell you how much water you had to apply for that crop. So crop coefficient is important. Each crop takes water a little bit different and a little bit more, and I'll show you a table, I think, for that. So non-uniform soils, we talked about that. We talked about wind drift. We talked about water soils or plants, distribution variation, and non-uniform soils. We've pretty well covered that so far. So I'm not going to go back into that. So gross irrigation requirements. Now everybody understands the difference between gross and net. The gross is what is tied specifically to an irrigation system, what the efficiency of that irrigation system is, and actually applying the net amount you're trying to get to the soil. So like I mentioned earlier in the presentation, real irrigated ground, if we can get it up to 40% efficient, we're lucky. So if you want to put on, let's say 50% efficient, and you need to put on 2 inches of water net, you have to apply 4 inches of water to get that 2 inches, because the efficiency of the system just can't apply it that effectively. You lose tailwater runoff, deep percolation, those types of things happen. So knowing the efficiency of your system is critical. The more efficient you can apply the water, the less water you have to apply, which ties back to pumping time and energy savings and costs. So it's really important to understand that. The range of efficiency for this type of system, 70, and I'll show you the example, 75 to 100 with 80. Assume an application efficiency of 75% gross amount of water needed to get 3.2 inches into the soil. Gross 3.2, net is 3.2 divided by 75%. You need to put 4.3 inches of water to get that 3.2 on the ground. So knowing the efficiency of your irrigation system is critical, and I'll show you a table here in a minute. And this is the amount of water the system needs to be designed for to get the 3.2 inches on the field. Typical irrigation system efficiencies are found in the irrigation guide and also found online or measured in the field. Now, that measured in the field really comes into play, and I just want to concentrate on this for a second. In your operation and maintenance plan, which should go with every irrigation water management, the operation is a part you're showing them how often to put the water on, what your frequencies are, but the maintenance of the plan, an impact sprinkler in the Columbia Basin has a life of about 5 years. That the amount of sediment and stuff in the water and things wear those nozzles out over time. And so if you started out with like 11/64 inch nozzle and all of a sudden it's up to a 5/16 or something, the difference could be that sprinkler head putting out 3 gallons a minute, and when it's wore down would put out 5 gallons a minute. Mark a different amount of application rate, which is going to be detrimental to the system over time. And so what I always carried with me was a packet of drill bits, like 1/4 inch up to 1/2 inch, where you could actually take it up and stick it in the nozzle and tell if it was really the nozzle size it's supposed to be. And if it's wearing down, replace it. It's inexpensive to replace, takes a little bit of time, but that's part of your irrigation water management planning with the producer, is maintaining that system over time. And I think that 5-year lifespan is a rule of thumb that you could take to the bank. And if they're not replacing those nozzles or nozzle packages in that period of time, they're going to have problems down the road. So maintenance, operation and maintenance plan goes along with the irrigation water management plan. These factors usually use an equation to calculate I'll kind of move through this and not reading, running a little bit long on time here. Each state has its own method and calculated values that are available for use for irrigation system design. This is called the evaporation transpiration rate, or ET. The ET is a water use rate by the crop plus the evaporation from the plant soil. So it's the crop, what it's taking up, and the evaporation. And this is the amount of water the plant uses. And this is where your meteorological stations come into play across the country. Every one of these red dots is a climate station. And those climate stations measure soil temperature. They measure the evaporation rates, just all kinds of factors that come into play. And in Washington State, here's the ones we have. And this is through the Ag WeatherNet system through WSU. Each one of these numbers, if you get this system, and I'd strongly recommend you register with them, and anybody can do it, and you can get online and you can click on any one of these stations, and the closest to where you're irrigating, you can see a bunch of them in the Columbia Basin, and it will give you those ET values on a day-to-day basis. So a consultant, irrigation consultant, will call into these every day and find out what the ET rates and kind of track that for growers. So this is a valuable piece of information for you to tie in and get familiar with the use of these stations. There aren't too many over on the west side, but still you could use these as an indicator. And like I said, I'd strongly recommend you to become a member of this group. And there's all kinds of other valuable information on this AgNet site that would be extremely valuable to you as part of your continuing education into this. And there's really good descriptions on how to use the systems, the functionality, and all those things would be super important for you to know. So the net irrigation amount of water is the difference between field capacity and the moisture level selected when irrigation is needed. Available water capacity times MAD will give you that. Maintaining constant moisture through the season is generally not practical. Ideally, irrigation is started just before the selected MAD level is reached, or when the soil will hold the irrigation application plus expected rainfall. And I keep putting rainfall in here because for people on the coast, it's an important factor. You don't want to be running the water through your sprinkler system if the soil profile has already been satisfied with irrigation rainfall. So here's the if you learned anything today, this might be the one thing to take home. If the total soil moisture, I kind of in 40%, it just gives you that gross amount of water that you have to apply. And the other factors you take into play is leaching and temp modification, effective precip, groundwater contribution, and change in soil water content. Frequency of irrigation. How often the crop gets irrigated depends on how much water is available and how fast it is used. The amount of water available is the amount that is in the soil. The rate it's used is based on the ET value. Frequency can be estimated by dividing the net irrigation that you're going to apply by the evaporation or the ET level, and that gives you your irrigation frequency. And so here's the formula. Net irrigation that you're going to apply plus the ET for the day. And that gives you how many days you're going to have to get across that field and back to the point of starting. And by the way, for a big issue with wheel line people, that let's say they've got 12 sets to get across the field. And they've got three irrigation systems. So it's 12 sets, they get across it in 4 days. If they go to the end on that fourth day, and then just rather than take the time to take that system all the way back up to the beginning of the field where they started and start irrigating from the bottom back up, they'll over irrigate and under irrigate the top part of that field, if it makes sense. You got to take those hand lines and wheel lines back to the starting point and start irrigating again. Don't just irrigate reverse back up the field. That seems like a simple concept, but I see it all the time because it's labor. It takes labor to do that, but it's well worth your time. So here's that example. What is the max irrigation frequency for the example above? Near irrigation was 3.2 inches. The daily ET from your weather station said you're losing 0.4 inches per day for that particular crop. So your frequency would be 3.2 divided by the 0.4. You can get over this field every 8 days. And again, that gets back to designing your irrigation system. But this is during peak period use. Keep that in mind. You're designing your system for the peak period use of the year, typically July and August. For us out here. So you're designing that for that period of time. And so this crop will use up to 3.2 inches of water in the profile in 8 days. Then you go back to the beginning of the field and start replenishing that as you go down. So that this little piece right here is super critical to take care of before that grower ever comes into your office. You've done your homework and say, boy, when we design this plan, this is your frequency. And then you start talking about labor too. It takes time to move a wheel line, a hand line, and so you bring labor, and it may be worth it to them to put a little more system out in the field to reduce this. Instead of 8 days, take this, put another piece of system out there, take it down to 6 days, and so you got 2 days off to maintain the system, or rest days you don't have to worry about it. So there's all these little nuances and side things that come into play that, by the way, typically a vendor will not tell them. A vendor is hired to design an irrigation designer, and they do a great job at it, and they'll tie it to that peak use, but they won't tell you how to manage the system. You have to either hire a special consultant for that or learn how to do it yourself. And here's a plan years ago that I did, but it just breaks the year down into April, 1 inch of water. Your crop evaporation is only 0.03, but look in July, this is how much the plant is taking, but in July, it's taking 0.21. So this is where you would put your irrigation frequency is 3 days needed. So if you had a little chart like this put together as part of your irrigation water management plan, it would be super important because then the grower could look at it, and it's not absolute. We had a heat event a couple of years ago that blew us right out of the water. No system out here could keep up with it. And this is the other thing, I don't get into this too much because it gets into politics with climate change. Climate change is real. I can't say it anymore. And it's only going to get, I'm looking at the consumptive use tables in the Columbia Basin, and I already believe they're off. But I don't have the time or the equipment to do the scientific evaluation. So I'm working with Tyler down in Prosser and some of those guys at WSU to take another look at this. But I'm pretty sure that these consumptive use tables are going to be outdated. So when I design a system now, I build a little more flexibility into it, what I call a little bit of over design, just to compensate for that coming in the future. And here's a design I did years ago, and it has all the pieces in here. And you can use this for evaluating a system as well. Average operating pressure of this system is 38 pounds. And of course, I don't expect you guys to be designers, but these are factors that go into evaluating a design. The nozzle size, what each head will put out. And this, again, if it's a 13/16, you come out here 5 years later and all of a sudden this nozzle's putting out 8-9 gallons a minute, it's time to change that nozzle. Your sprinkler head spacings, 40-50. and I usually design these at 40, 60, but this was in an area that had strong wind gusts during the critical parts of the year. So I tightened up the spacing to 40, 50, which means he had maybe a little more equipment, but I took into consideration the wind effects, and I just built a little bit more of a robust system. So how many laterals? 2, what the length of those are, the diameter of the pipe, and this was a wheel line, a main line of 2,600 feet to service at 6-inch PVC, 160 pounds per inch is what it can take for pressure range. I designed a pump for 30 horsepower at 475 gallons a minute. And you'll hear this term all the time, head, foot of total dynamic head. That's the energy required by that pump to push against gravity, for any lack of and that's another thing to keep in mind when you're looking at a field. The slope comes into play. If the pump's sitting at an elevation of 1,200 and the last nozzle, the highest point on that field, the nozzle would have to be operating is at 1,300. That's 60 feet or so of elevation gain that you have to add on to that pump horsepower to meet that need, because you got to get that pressure to the highest nozzle on the field of the system. So sometimes they miss that, and they try and play games a little bit to keep the horsepower down and the cost. And when they can only get 30 pounds to the top of that field when they really needed 40. So you need to pay attention to that a little bit as well. But this has all the elements in here that you need to develop an irrigation water management plan, because you know the precip rate, and you know the laterals and all that. So and there's some of these examples in the irrigation guide as well. So here's the irrigation efficiencies for different types of systems. You can see our surface irrigation systems, a level basin. We don't use any of those. I'd be hard pressed to find one in the state of Washington. But we do use furrows and corrugations, range 50 to 80. You're never going to reach 80. I don't care what you do. I design these systems at 50%, and I never get up to 65 on those. Surge, if you employ surge, I would take that up to 60% or so. But these are things you'll learn over time. Micro irrigation, of course, is a very efficient system of getting water to the field. Most of ours out here we deal with is wheel lines and hand lines, and center pivots. And I did say earlier that those dragon line or mobile drip irrigation will reach 95% efficiency. Your lateral moves versus your circular on your sprinkler systems are somewhat easier to manage, because they're just moving in line straight down the field and not in a circle. Your planting patterns and other things can come into play. Sometimes when you're planting under a center pivot, they got to plant in a circle as well, which some of the GPS units or the auto steer units have some real challenges with. So deficit irrigation, this might be something more where you have interruptible water source. Some of that happens in the Columbia Basin, where if water really got tight, you might be cut off later in the season. It doesn't happen once. I've seen it happen once. But you have to take into consideration some of this deficit. On the coast, this might come into play more often, where you have a lot of precip and you're basically just kind of making up the difference or lack of water. Your irrigation water right only allows you to use a CFS versus two CFS or something. There's a lot of reasons this comes into play. But we don't. Go ahead.
We have a question in the chat. What is your opinion of the NRCS FIRI tool, the Farm Irrigation Rating Index?
I think it's a really good tool for starting to figure out, what your systems will do. It's not that challenging to use. That's FIRI if you guys are looking for it. And I've used it with new growers to evaluate the performance of existing systems in the field and where we need to, bring those up a bit. So that again could be a training session for FIRI, using those tools we could spend an hour on that, and I think it would be value added as subsequent trainings. But I like it. You have to understand the limits of the tool, and and have some knowledge on how you're going to use it. And then it's an effective conversation starter, let's say. Ways to reduce the amount of water required to be maximized. Again, the rainfall, deficit or partial, selection of crops with low water requirements during normal peak use. And we see this some in the Odessa aquifer, where I'm working with growers where they might have 5 fields and they've only got X amount of water. And 4 of them, they're all, if they used all 5 with high peak use like alfalfa, they might not be able to have enough water to do that. So I say, why not throw a wheat crop in, which has a very short growing season, typically harvest in June. So, those types of things, you need to look at the rotation to make sure that your water that's available to you will meet the peak period use when everything's in operation. So that's an important thing to keep in mind. Selection of drought resistant crops, is something that could be used. Alfalfa hay is very, very forgiving. You might not reach that 7 ton you want for the year, but maybe 6 or something would be adequate if you're using less energy and inputs. Irrigation just before critical growth period of the crop to minimize critical. We've talked enough about that already. Use of state-of-the-art irrigation scheduling techniques, and we're going to talk a little bit here in a minute about that. I'm going to start moving a little quicker here. I typically teach this class in 3 days, and I spent the last 3 days condensing it down into 1 and 2 hours. So anyway, no excuses. Use tillage practice to allow maximum surface, follow intensive crop residue management, reduce irrigated acreage, which can be adequately irrigated with available water supply. Other things, quality and yield can be negatively impacted by reduced cooling is used to reduce plant stress, delay bud development, slow down fruit development. This is in crops. We use a lot of overhead for cooling the orchards down to prevent sunburn and other things. So there's techniques, again, in the management you can use if they're looking into cooling. Frost control is another one, can be effective down to 25 degrees. And these are usually overhead sprinkler. They have to be overhead sprinkler or spray systems that come into play. So if we're working with a new orchardist, we're basically designing 2 systems, one under tree and one over tree for various, for these specific reasons. Salinity, we talked about that. I'm not going to go into more, but down here, this ionic concentration solution, calcium, manganese, potassium. Some of our deep wells are picking up poor water where they're bringing salts and different things to they're affecting soil health. So I would suggest, if you're working with people on these deep well systems, that they pull water samples and determine what the chemical composition of those are, because they may have to mitigate for that for sure down the road. You might even be able, might plant a crop and basically not be able to meet your production requirements. Most of the water requirement comes from irrigation. Okay. Salinity and salinity. Seasonal water application. We talked about that. Only small areas of systems can meet the crop water need at continuous level for the season. I think we covered that sufficiently. Usually there's enough water, the system would be too expensive for whole field conditions. If the system you're putting on, this comes into play if you got a grower that's coming in and wants to put a wiper on a field. Let's say typically field for a full irrigation under pivot is 130 acres. And a wiper would only irrigate 65 acres of that, but it costs the same. You put the same amount of money into the hardware and the pump and all that to irrigate half the acres. That's where the economics comes into play. And I build that into my pre-planning report when I bring the owner in, you understand the economics of this. Center pivots, 1,300 foot center pivot now bouncing up against $150,000 to $200,000 to put that on the ground, and 130 acres versus 65. So something to keep in mind in order to calculate the water supply. And this is a formula you could use if a grower comes in and asks and says, I've got X amount of water, which is your Q, the flow rate of a half a CFS. And you can calculate how many acres you could irrigate with that. And that's a good starting point, because if a grower comes in and says, well, I've got water rights from this stream for half a foot of water, or about 250 gallons a minute, and I want to irrigate 200 acres, a red flag better go up, because they're not going to have enough water unless they're just using it for supplemental purposes. But if they need a full season of irrigation, they're going to be irrigating about half that acreage. And so that all comes into play, but you can use this formula to determine that. And so here's an example. An irrigation system runs for 24 hours on a 100-acre field. How much water must be diverted to the field to apply 0.45 inches? And so you got QT day, and you're looking for Q and time, and you're going to have that 0.45 in 24 hours. And they need 1.9 CFS to make that happen. And so back to my example, if they only had 1 CFS, they're going to irrigate 50 acres. And so that, again, is part of your pre-planning with that landowner. Peak versus average. And again, I'm not going to go through all this, but there's a quick way to average, but there are too many average days in a month. The more accurate method is use the following equation: your evaporation transpiration times your monthly peak use times your net irrigation. And these can be found again in the irrigation guide. In this example, 10.25 inches. Net irrigation is 2 inches, 0.4 inches per day, and your average use rate would be 0.34. So there's ways to calculating that. And again, if we're going to get down into that detail, we need to have specific sessions that talk about these specific topics in more detail, but I just don't have time today to go through all that. The highest ET days are hot, dry, and windy. The lowest are cloudy, cool, and rainy. Even the hottest month of the year, both types of days are possible. By using the average ET for a month, this is an average of hot and cool for the 30 days. If the frequency of irrigation is less than 30 days, there's a chance for hot or cool days for either could happen. And it gets into the frequency a little bit more. Wind and drying patterns, you really got to pay attention to this early in the season, where you got typically bare ground conditions. You got a lot of wind sucking the moisture out of the profile. So it's important to pay attention to that. I'll show you a graph here in a second. Get to the graph. Here's at George Washington using a evaporation station. You can see what a growing season looked like in January all the way through these peaks. You can chart it out. And there's your peak consumptive use period right there in July, like we said. And so you're going to be designing for that. But sometimes mapping things out really brings it out to the grower you're working with, so they can visually see what you're talking about. And we talked about the crop height on selecting an irrigation system, tolerance to spray, frost and cooling, soil intake rates on your center pivots, drainage and stoniness, the quality of your water. We talked about that, the reliability of your water. If you're in the Kittitas Valley and the Teanaway goes dry late in the season, you're in trouble. Climate, wind, and rainfall, field shape, economic, local laws, water rights, and operator management are also factors that can affect the type of system installed. You know, we're working on systems out here now where we have to bore under highways to put them in and stuff. So understanding some of the local laws and things you have to, and where utilities are for pumping stations, all those things have to be taken into consideration. Sometimes running power to a pumping station can be as costly as the irrigation system itself. It's very expensive, even if they have the amount of power you need during that part of their operation. Surface, flood, furrow, I did all that already. Sprinkler. I would talk about these in more detail sometimes. Slope limitations. Sorry for going through these fast, but I'm at my time here. We won't have any time for questions. This PowerPoint will be available to you. I'm not going to go through all these again. I had, this is what you taught. Windsurfer's another program you can get that is pretty good for evaluating your farm. In fact, I like this a little bit better. Fury is a complement to this, but you can run simulations. And this is supported by ARS, USDA, and Arid Land Agriculture Research. And so you can use this tool. So pull it up and take a look at it and see if that would work for you. I'm not going to go through all these again. Sprinkler irrigation, periodic move, we talked about. You're seeing a lot of these out here, subsurface drip SDI systems, where they actually pull the tubing in next to the plant, below the plant. These are like MDI systems. They're very efficient. The difference why we're headed towards MDI is these systems only last 1 year. At the end of the year, you got to pull all this tape up, and the big piles of this stuff sitting around the countryside. So MDI eliminates that. MDI system could go, and this is MDI that I was talking about, mobile drip. And I think this is going to be the future, where these drip lines come down off this feeder line or drug on the surface and only wet next to the plant. You see all the good residue between the plant here. And this is on a ratcheting system. So as the crops are high, like corn, you can ratchet this line up into here. So you can put this down lower or shorter. We're trying to get some of those into the basin right now. Center pivot design, water management, and irrigation guide I talked about. I want to show you one more thing before a tool that you might want to employ. See if I can get that up. Come on, here it comes. This is a fantastic tool that NRCS has available. That has, you can develop an IWM plan off of this. Really has all the crops, soils, moisture levels, and centibars. Everything's in here. But for the planning purposes, you know, I'll just run through one real quick for you right here. Put the name in and the location. There's drop down menus. I'm going to use, this is for Mattawan, Quincy. I'll use Quincy. The crops are all in here. So we'll just use, just grab one here, dry beans. And all of a sudden it tells you what the root depth is in the zone, the management allowed depletion for that crop, the ET for the year, and the monthly ETs are in here. And then you can come down here and you can pick your soil. And it puts all your soil data in there. Soil depth, available water holding capacity for that crop, root zone, texture of the soil, soil intake rates are in here, and it's perfect. Then you can come down here and start. The grower told you, well, I've got 600, I've got a foot of water on that system. And all of a sudden it tells you that's 1 CFS, and you can put in the hours of operation, the percent on the timer, say 24 hours in here. of the time or at 100%. Estimated efficiency, 85%. Sprinkler diameter. You can go through and it puts all this stuff in for it. And I'm not going to have maximum application. Let's say sprinkler application time, 23 hours. System application. And okay, on here, so it starts filling in stuff for you. Under a center pivot, putting it on that fast, there's a potential for runoff on this. And so you can keep going down peaky 2.43, put in here. And it'll come down here, and this, I have a little bit problem with this. Gross, it didn't divide it, so somewhere I haven't put anything in here. But this could be a whole session in itself on how to use this system and have it available when the landowner comes in. This top part, you could design any system off. It doesn't have to be a circle. It could be, it could be a wheel line, hand line, because you have all the data in here available that you need to design that system. So I'm going to end there. I've already gone 5 minutes over and I haven't gotten through everything. So I'm going to turn this back over and answer any questions. Leave a part in here for you to ask us some questions. And I'm sorry I rushed through that last part, but again, I could have talked to you all day about this. And anyway, John, you can take it from here.
All right. Well, it looks like the most popular question is about that tool, the Excel tool. So maybe we can get that loaded up either on the CTD website or in the efficiencies web page, or both.
No, before you go there, John, these are set up by county and soil survey.
Okay.
So if you're in Walla Walla and you want this tool, you need to go to NRCS and make sure that's set up from the tool for the tool in their counties, because these are specific to what we've got here. So it's going to be important to make sure it's set up for local.
Okay. All right. So the local NRCS offices should have this tool available.
Yeah, I'm assuming. I've been away from it for 7 years. I don't know. So, but I would start there and ask them, because that would be the tool that I would think that these guys, I went through all that previous stuff, getting down to that tool, but they know at least what those elements are in that tool and they can use it effectively. So Dinah got it from the local NRCS office. They should be willing to do it. So, yeah.
Perfect. And then Joe Holtrop has a question. Irrigation guide assumes planting in April and irrigating through the growing season for most crops. On the west side, you might be able to plant the same crop in April, May, or June. ET is different for those months. What do you do? And what about irrigating in high tunnels?
Well, let's start with the first one. If you're going to plant in April, you'll use the ET values off your climate station, and they'll vary for April, May, and June, and just use the climate station data for the ET rate, and that should get where you need to be on your net irrigation, gross irrigation, frequency. So it doesn't matter what time of the year, just pick the month for that ET value. And it won't vary a whole lot through the season. I would think for you guys on the coast where your temperature variations can be up, but they're not going to be as significant as they are over here, where we go from, 50 degrees an hour, they're planting peas in Mattawa. And by the time they harvest those, they'll be up to 80, 90 degrees. So just pay attention to your local weather station. And if they don't have those, we need to talk offline. Now in a high tunnel and interior, of course, your evaporation, your temperatures are going to be a lot higher. I would actually use a soil moisture monitoring probe in those high tunnel systems, where you can measure the soil moisture, either with there's several handheld systems that you could use in that. and irrigate according to the soil water potential that you get off those measuring devices. Because you got a microclimate. You're basically got a jungle in there where the temperature can be significantly higher. Your everything's going to be higher in there. So get a good soil monitoring probe.
Right, right. And those soil moisture monitoring probes are cost eligible as part of the cost share, the application system, cost share application. So
Watermark sensors are
Yep.
pretty typical. And I had a whole presentation on how to set those and put them in the field and use them and measure them, but that's down the road.
Right. So that's a great segue for me to say, please reach out with, I made a note every time Harold said that's a training session. And I added the basic water rights course that I've got a lot of contacts at ecology. We could set something up if you want to delve a little bit deeper in. Harold did a great job of getting, covering those, kind of a checklist of the things you need to pay attention to. We can beef that up if desired, but also web soil survey, the NRCS theory, and then the spreadsheet plan that and of course that may or may not exist in your NRCS or local office. So, and I guess where I'm getting to is that if you'd like training on those, I can work with Jan and CTD and get some resource experts together. It might be Harold again, which would be perfect. Harold, you did a fantastic job. I sure appreciate your wisdom and expertise here. So reach out for the training needs. I'm putting together some resources on the efficiencies webpage. There's links to the Washington Irrigation Guide up there, and the IWM practice code documents are, they're not there yet, but I'm working with staff over in Olympia to get those put up on our webpage, and then we can probably also get them up on CTD as well, but we'll figure something out. So anything you need, if you have questions, give me a call and I'll figure out who has the answer that you need. I might be able to answer some myself, or we'll get you to Harold or somebody else. Yeah, happy to help make your program successful any way we can. So yeah, I don't see any more questions in the chat. Jan, do you want to add anything before we close this out?
Yeah, no, thanks. I think you wrapped it up really well. Thank you so much, Harold and John, for your time today. And it sounds like there are a lot of good follow-up trainings. So Harold will maybe keep you busy with helping get this.
Well, I didn't necessarily volunteer for all those right now. And we did talk about having an irrigation field day
Yeah.
at one
Oh, yeah.
point. And if that was to come to fruition, a lot of the watermarks and sensing devices and system stuff could, when you're looking at it in the field, and seeing it happen, it's pretty effective.
Yeah. Yeah, I guess, yeah, man, I forgot to write that note, but I had made write that down. That's probably the biggest question I'd have about training. If you want to take this to the next level, please reach out and let us know if you want to get some dirt in your boot treads and get a real feel for what soil feels like at different moisture levels in a site-specific training on real ag ground under a real sprinkler system. Please reach out and let us know. And Harold's got an amazing curriculum that he works with his staff on, and we'd like to know if that's something that folks out there are interested in. A little bit higher level, 1 or 2 days, depending on, I don't know, we'll figure it out. But again, Harold's, like he said, he usually takes 2 days. I know this was a lot. This was a fire hose, a lot of information. For me, I'm a, visual and hands-on kind of guy to learn, and it would help me understand some of these principles if I were out there. So feel free. Yeah.
yeah, please let us know what training you need, and especially if this in-person one sounds good, and we can always do webinars, you know, on these specific tools and things like that too. So let us know what you need, and we will post this recording on the website, both the commission website and the CTD website. I'll get this processed just here in a few days and get that up and let everyone know when it's up there. If you need to refer back to it. Yeah. Thank you so much for being here today, guys. And we
Awesome.
appreciate it. And thanks to everyone for joining us.
Fantastic. Thank you all, and have a fantastic day.